everyone. Today, Carly and I are going to be going over order of growth and order of growth classifications. As programmers gain more experience using computers, they often start to use them for more complex problems or more difficult problems, or use them to process large amounts of data. This often leads to questions about the efficiency of a program that otherwise wouldn't have come up if you were doing a much more simpler program. These questions include how long will my program take, or why is it taking longer than expected, or why does my program run out of memory so fast? To answer these questions, programmers use order of growth classifications to determine how fast a program is going and if it can be faster. Order of growth is a mathematical representation of the total running time of a program based on the number of inputs. We often use tilde approximations in the form g of n tilde a f of n, where f of n is equal to n raised to b log raised to c n, and refers to f of n as the order of growth of g of n. Programs are often based on a few structural primitives, for example, loops, nesting, method calls, etc. So order of growth of the cost is often just a few functions of the problem size n. And I said order of growth of cost because when we are coming up with these mathematical representations, we keep two things in mind. One, what is the cost of executing a statement, and how frequent is the execution of that statement?
So there are different mathematical models that show the speed of a program based off n, the number of inputs. So the example function is just the entire function that shows the speed based on the number of inputs. In this case, for an example, is 2n squared plus 4n plus 8. The tilde approximation just shows the fastest growing aspect of the code with the numerical coefficient in front of it. So it would be 2n squared, because n squared grows the fastest out of those three terms in the example function. And then the order of growth just shows the fastest growing aspect with no numerical coefficients in front of it. So in this case, it would just be n squared. So the order of growth is about the running times. And here's a comparison of some common running times in code. So first, on the left is a chart with different run times, some examples, and on the right is a graph showing the runtime's speed as n increases. So the simplest, fastest order of growth is 1, called constant, because it is constant and not affected by n at all. An example of this would be just a statement such as a equals b plus c. No matter how many points of data are inputted into the code, a equals b plus c will take the same time to run no matter what, and that's shown here in purple as a constant line on the graph. That is just flat. Next, another important one is log n, called logarithmic. And an example of this is binary search. So in binary search, you have the number of data points inputted, and it is divided in half every time until you get the one point you are looking for. And the constantly dividing in half is a logarithmic function. Log n is pretty efficient. It's shown here in dark blue, log base 2 of n. As n gets to really big numbers, the runtime does not increase by a lot. It still increases, but it's not by a lot, so it's pretty efficient. Another important one is n, which is linear, and this would be a loop. So for example, if you just have a for loop through the number of points inputted, that would just be n, and that's shown here in green as a line with slope 1, straight line. Next, another important one is quadratic, which is n squared, and this would be a nested loop. So for example, if you have a for loop inside a for loop, because you're iterating through a data set twice within each other, such as checking all pairs, then that would be n squared, shown here in red. You can see when n is small, n squared isn't that big, but as n increases, n squared does increase by a lot. And so for large n's, n squared is not very efficient. And last is exponential, or 2 to the n. This would be checking all subsets, and 2 to the n is extremely inefficient. You want to avoid that at all if you can. You can see in the dark yellow here that 2 to the n increases by a lot as n increases even only a little bit. So really try to avoid that.
So here are a few examples of some code snippets where we can determine the order of growth. So as Carly mentioned earlier, when a code snippet is linear, it often involves for loops, and it runs through the entire data set. Now both of these examples are linear. This is because in the first example, the for loop runs through the entire data set n and multiplies by 2, so it increases, and the running time of this is linear. This is the same for this one. It runs the program and it goes through the entire list n and divides by 2 as it increases in the as it goes through the data set.
You can use order of growth to determine how efficient a code is. In this case, we're looking at two codes called twosum and twosum fast. They do the same thing. They take an array and see how many pairs in that array sum to 0. And they have different orders of growth. So on the left is the regular twosum, the count method, and it has nested for loops that iterate through the array twice to check all of the possible pairs. And so since it is nested for loops, that means it's a quadratic or n squared order of growth. Now for small n's, that is not that bad, but for as n increases, n squared increases by a lot. Here on the right is twosum fast. Now this, instead of using nested for loops to iterate through the array, it sorts the array and then uses binary search within a for loop to check all possible pairs that could potentially sum to 0. And so, as we said before, binary search is dividing in half each time, which is logarithmic, and it's inside a for loop, which is linear. So that would be log n times n, or an order of growth of n log n, which as n increases is less than n squared. You can see in the graph from earlier that n log n is this orange one right here, and n squared is the red one, and n log n is clearly less than n squared. And so here are the codes for twosum and twosum fast. The main in both is the same, so they have the same values in the array, so that is not going to affect the time. And then we use the stopwatch class to count how much time elapses for each of the programs. So here is the count method that finds the pairs for twosome fast, and here is the count method that finds the pairs for twosome. And so if we run twosome, we as the user get to choose the number of inputs. So if we choose 1,000, then the elapsed time is 5 milliseconds for twosome, and for twosome fast, if we choose the same number of inputs, 1,000, the elapsed time is only 1 millisecond. Now, if we increase n to 10,000 for twosome, the elapsed time is 83 milliseconds, and for twosome fast, the elapsed time is 3 milliseconds. So as you can see, twosome fast is increasing at a much, much smaller rate than twosome, and that is why it is more efficient. And they still give the same answer. The number of pairs was 10 every time because that's what the array was filled with, to make it the same every time for comparison. So as you can see, order of growth is very important in how efficient code is run, and you want to reduce the order of growth as much as possible when you're coding. Thank you.